myself Dr. Preeti Jagwani. I am from Department of Computer Science, Aribhat College, University of Delhi. So presently in our previous lecture we studied about the problem of, or we explored the problem of median and order statistics, and within that problem we have looked into two subsections. One is finding the first order statistics, that is the minimum a trivial algorithm. Similarly, symmetric to it, the finding ith order statistics, which is maximum, again a trivial algorithm. And we have also seen how not the asymptotic analysis, but yes, number of comparisons can be reduced if we talk about finding this minimum and maximum simultaneously. Now we look into our further whatever leftover section of the problem of ith order statistics, which is the randomized select. If we talk about the problem of randomized select, so the randomized select says that we need to look into the ith order statistics, or we need to find the ith order statistics, and this problem is our randomized select. Now, why are we calling this select problem as randomized select? Because this is based on the partition strategy which was used in quicksort. So, what was this strategy? Let us try to recall. So, in quicksort what we did was we chose a pivot element, maybe let us say randomly, and partitioned the whole array around this pivot. So, whatever and that was done recursively. So, for example, so the sorting was done actually recursively. So, partitioning the array around this pivot is going to give us the array into two partitions, one which is having all the elements lying on the left side of the pivot, and all those elements are lesser than the pivot. On the right side of the element, all the elements which are greater than the pivot, although these elements are not sorted. Elements on the left in the left array are not sorted, elements on the right array are not sorted, but we have pivot at its right position. And then if we look into, or if we employ this partitioning strategy which we used in quicksort here in randomized select algorithm. So, we will randomly choose a pivot element, we will partition the array around this pivot, and if our pivot is our the element which we are looking for, we are done with it. All otherwise we will recursively search in the appropriate search array, which is if we are looking for an element which is less than the pivot, will definitely be found in left side. If we are looking for an element which is in the right, which is more than the pivot, will definitely be found on the right side of the array. But the question comes up, why are we calling, or why are we using this randomized select? Why random? Just to ensure that the expected performance, please mark the words, just to ensure that the expected performance is good, and we by this we will be preventing the worst case scenarios from consistently occurring. And this is what we did in our kind of randomized quicksort. We have gone through quicksort, then we jumped into randomized quicksort. Why random we have taken? Just to ensure that the expected performance is good. So, here we are going to use that randomized partition strategy. What is that randomized partition strategy? So, in terms of algorithms, if we talk about randomized partition strategy is we have an array and the lower limit is p and the higher limit is r. So, we have an array A starting from p to r. So, randomized partition A comma p comma r says selects a random element from this A starting from p to r as the pivot, and we need to rearrange this A, P, R such that all the elements let us say A, K, where K belongs to, or K K is between P and Q, which are less than pivot, and all the elements A of K where k is ranging from q to r are greater than pivot, and finally we will be returning the final index q of the pivot. So, this is actually our we can say a randomized partition strategy, that taking the group of elements lesser than the pivot on the left side and taking the group of the elements which are greater than the pivot on the right side, although this group is not ordered as I have told you. Looking into time complexity, that we have seen in our earlier lectures also, is order n for a sub array of size n. And if we look into this pseudocode of randomized select, which is ultimately using randomized partition, how that pseudocode goes as randomized select, we are going to do with 4 parameters with 4 arguments instead of 3. So, one is a our array, the limits p and r, because these are the limits which are going to change in our recursive calls, and the I, which is the index of the element which we need to find, or we can say simply we can say the desired rank. So, the input is array A, start index p, ending index r, and the desired rank I. So, what is going to be the best case? If p is equals to r, which is array of one element, then you need to return a of p. Or okay, this was the best case, but what do we need to do? We need to partition this array A starting index p and ending index r with the help of randomized partition, and whatever is the result of this randomized partition will be stored inside this q, which is our you can say is now the pivot element. Now, we are going to calculate the rank, which is q minus p plus 1, which is the rank of the pivot within this array, and then we will be checking if my I, which is the desired rank, is matching this calculated rank or is matching with the what we can say the rank of the pivot element, then we are sorted in one call. We will be returning a of q, which is y, because pivot is the desired elements. But if this is not the situation, then either we will do this recursively for the left array, or we will do this recursively for the right array. So, either we will recurse left or we will recurse right. So, if my I is less than k, that means the desired rank which I am looking for. So, for example, my pivot is, let us say 15, and the rank which I am looking for is 7. So, 7 is less than 15, then we will start this randomized select with the newer parameters, or we will call it recursively with the parameters a, p and q minus 1. So, starting from p till q minus 1, all the elements we will do this randomized select for this ith desired rank. Else, if we look into this, that the I is greater than k, that means the desired rank is greater than the rank of the pivot, then we need to return, or we need to call our randomized select with the parameters a, q plus 1, that means all the elements which are on the right side of q, q plus 1 till r, along with the desired rank, which is I minus k, because we need to adjust I for the new subarray. Now, this is very important. We need to return the randomized select with a, q plus 1, r and I minus k, not I. So, here you can see this on the screen, that if we need to recurse left, then the call to randomized select says a p q minus 1 to I, which is starting from p to q minus 1. If we need to recurse right and so recurse left starting from p to q minus 1 is fine, and the desired rank is I. That is the point to be noted. If we need to recurse right, we will be recursing in the right portion which starts from q plus 1 to r, that is fine. But now the desired rank is not I, the desired rank is I minus 1, because we need to adjust this I for new subarray. Now this is something which is important and which we need to take care of. Now let us take an example walkthrough for this randomized selects. So here we have an array A which is 3, 2, 9, 0, 7, 5, 4, 8, 1, 6, which is 10, and we need to find the fifth smallest element. That means fifth order statistics where I is equals to 5, that we need to find. So initial call to this randomized select will go with A 1 comma 10, which is the lower limit and the higher limit, and the 5 which is the value of I here, and let us say randomly we are choosing A7 which is nothing but 4 as the pivot. Now we need to partition this array around this A7 which is 4. So all the elements less than 4 will be on the left side, which are 3, 2, 0 and 1, and all the elements which are on the which are greater than this pivot are 7, 5, 9, 8, 6 are on the right side. Although I am repeating again, the left subarray, neither the left subarray nor the right subarray are sorted, and our pivot is at index 5. Now let us calculate the k, which is 5 minus 1 plus 1, and this is going to be 5. And here luckily in our kind of first walkthrough, we have got I is equals to k, and hence we will be able to return A of 5 is equals to 4. If this would not have been the scenario, either we would have recurs in the left subarray or in the right subarray, depending upon if your I is greater than k or your I is less than k. Both the ways we need to do this. So this was one particular, we can say, algorithm of randomized select we have seen, and we have also seen the example walkthrough. But if we talk about the worst case analysis of randomized select scenario, now we can say that in worst case this can happen that the chosen pivot is always the smallest or the largest element in the subarray. That is a possibility, and recurrence relation in this kind of scenarios will be like T of n is equals to T of n minus 1 plus order of n. So every time your array is getting reduced by 1 element is reduced, and the partition obviously is going to take order n times. So the recurrence goes like T of n is equals to T of n minus 1 plus order of n. Now this is a recurrence relation. If we try to solve this, the simple solution to this recurrence relation comes up as T of n is equals to order of n square. But the point is, this is actually a rare scenario. Although this is the worst case scenario in case of randomized select, but this is rare. Why this is rare? Because randomization makes consistently picking the worst pivot, which is either the leftmost, or we can say the first or the last element in the array, highly improbable. So randomization makes consistently picking this worst pivot highly improbable. So because of this randomization, we can say we are saved. Now when we talk about the expected case analysis of randomized select, which we can say is yes, of course, based on the intuition, because here we are talking about the expected case analysis. So the key idea says, on average the pivot will split the array into roughly equal size part. I will not say precisely equal size part, but yes, roughly equal size parts. So even if your pivot is not perfectly in the middle, as long as it is within a constant fraction, let us say for example between the 25th and 75th percentile of the array, the problem size reduces significantly, because here not one element is being removed, but a portion of array is being discarded from doing the further work, or from forming the next level of next level size of the problem. And the sum of the geometrically decreasing series converges to order n. So, if we talk about the expected or the intuition case analysis, not the worst case analysis, and I have also shown that worst case analysis is every time getting the worst case is a little improbable. Here we talk about on an average scenario where even if pivot is not perfectly in the middle and placed somewhere between 25th and 75th percentile, the problem size reducing not by one element but significantly. That means it will become a problem size of which can be represented by a geometrically decreasing series. Now, it could be n, then n by 2, then n by 4, then n by 8, and so on and so forth. And these kinds of geometrically decreasing series converges to order n. So, if we talk about the expected case analysis, assuming that Tn is our expected running time, the pivot's rank k can be any value from 1 to n with probability 1 by n. Now, this is a very kind of we can say trivial statement, that the pivot's rank k can be any value from 1 to n, and each value here is having a probability of 1 by n. So, yes, we can say that T of n, which is the expected running time, is less than equals to 1 by n, which is the probability, summation of k is equals to 1 to n, T of max k minus 1 n minus k plus order of n. So, this kind of we can say a recurrence relation is something which we are going to get if we perform the expected case analysis more formally. And here if we take the maximum of 2 recursive calls, because the ith element could be in either of the left call, either in the left subarray or in the right part, which is the right subarray. This recurrence which I have just shown you is which is based on the probabilistic intuition, which is Tn is less than equals to 1 by n, summation of k is equals to 1 to n, T of max k minus 1 n minus k plus order of n. This recurrence can be shown to solve in T of n is shown to be solved in order n, and this is what order n thing which I was, or analysis which I was talking about, that yes, any ith order statistics barring first and last, any ith order statistics can be done or can be determined in the total time complexity order n, and the key idea behind this is the randomized selects. So, here if we take the summary, so expected time complexity is order n, worst case time complexity is order n square, space time complexity if you look into is order log n. On average for the recursion, stack is obviously is going to be formed, and order n in worst case if there is no recursion kind of thing. Pros, if we talk about, there is a very simple strategy to implement, and we have also seen how to implement this in our randomized quick sort, and very fast in practice for typical inputs that we have seen. But the other side of the coin, which is cons, is no guaranteed worst case performance. We cannot guarantee worst case performance. Now, this randomized algorithm which we just seen works well in practice. Now, what are we going to study is worst case linear time algorithm, which is actually a topic of theoretical interest, and it will guarantee a good partitioning element but it will also guarantee a worst case linear time selection. So, the algorithm here is known as selection in worst case linear time. Specifically, this algorithm is known as determine select. Now, the situation comes up, why do we need this? Why there is a need for worst case linear time? So, there are so many applications in our real world where guaranteed performance is critical. So, any kind of we can say application which is based on real time systems, or it is an application of competitive programming, and order n square worst case time is certainly not acceptable. Then what is the goal? We need to design a selection algorithm that always runs in order n time regardless of the input distribution. We have just seen one, but we cannot guarantee that that selection algorithm is going to run always in order n time. In case of worst case, that may end up in order n square worst time. So, the challenge is how to pick a good pivot deterministically, not based on the intuition, not based on the probability. So, the strategy here is known as median of medians. The core idea behind this is we need to select a pivot that is guaranteed to be good. That is, it will eliminate a constant fraction of elements from the search space, because what we need to do, we need to reduce the problem size. But how this can be done? So, the pivot which I am talking about, which is kind of reasonably good or guaranteed to be good, is chosen as median of the set of medians, ensuring that it is not close to any of the extreme, neither the left, the lower extreme, nor the right, the higher extreme. And the algorithm here which we are going to use is known as median of median algorithms, or often we can call it as the select algorithm. Now, what is the basic idea? The basic idea is we need to divide n elements into groups of 5, and we will be finding median of each group. Now, I am sure that every time your n is not a multiple of 5, then there will be obviously at least one group which is having a size lesser than 5. So, somehow we divide them n elements or n minus some groups of 5 elements and one group of elements which is having number less than 5, and we will be finding median of each group. We will be using select to recursively find the median x of those n by 5 medians, partition the n elements around x where k is equals, now we assume that k is equals to rank of x, and if I which we are looking for is equals to k, then we need to return x. If I is less than k, then we will be using select recursively to find the kth smallest element in the first partition, the same strategy, or we will be using the select recursively to find the kth smallest element in the last partition. Let us see this with the help of a figure. So, for every group of 5 elements, we have 2 elements which are lesser, one element is a median, and the next 2 elements is the greater elements. So, if we arrange them, this is a kind of figure which we are going to get, which is, if you can see all these group of 5 elements and take them in the columnar fashion. So, the first column represent one group of 5 elements, the green ones are lesser than the median which is shown in the peach color, and the last 2 elements are greater than the median. Similar goes with the second column, then third column, fourth column, and so on and so forth. Here you can notice one particular column in which there are not 5 elements. This will happen so many times, and it is having only kind of elements lesser than 5. And what are we actually looking for here? So, we are looking for median of medians, which is something which you can see is shown in the black circle. Now, all the elements which are, if you can see here on the screen, so we have some elements which are definitely lesser elements shown in one polygon. On the right side you can have definitely elements which are greater than this median of medians. So, by checking out this one portion of the problem size, we are actually reducing our n for further calls, and this is what the kind of a strategy where we are saying that we are having a reasonably we can say good or a pivot which is kind of guaranteed to be good. So, we are going to explore this whole strategy, but because of the paucity of time I will be taking it in the next lecture. So, here what we have seen in this lecture, after just a quick recap of your first order statistics and ith order statistics, we looked into the first order statistics and the nth order statistics. We looked into the ith order statistics, the algorithm we have seen, and we have looked into the expected case analysis of that algorithm. Then we had an intuition or just a rough idea of the new algorithm in which our pivot is going to be guaranteed going to be good, so as to eliminate the occurrence of worst case even if it is somewhere around. So, here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next lecture. Till then, take care. Goodbye.